So the next thing we're going to be talking about is ionic bonds, covalent bonds, polar covalent bonds, and coordinate covalent bonds. So ionic bonds, we'll start with that, is the donation of an electron. So if we have this right here has a lone valence electron, we only draw the valence electrons with these little dots, these Lewis dot diagrams. We're only drawing the valence electron. We know that this isn't just one electron in the entire molecule. And it's donating it. So we always will get ions, hence the ionic. We'll always have ions, and the only way to have ions is if you physically donate an electron. Covalent is sharing, so they just, join up together. Polar covalent bond is still a covalent bond, so it's still sharing, but we'll have a difference. So this would be nonpolar because there's no difference in electronegativity. Here HCl has a very different electronegativity. HCl, very, very different. Coordinate covalent bond is a little bit different. We can think of this almost like a nucleophilic attack. They share the electrons, but they actually share two of them rather than just one. Before, when we had, for example, there was just a sharing between both of these, and it was only one electron. So pretty simple. You probably wouldn't see covalent all that often for them to have you distinguish between the two, but it's something good to know. So the next thing we're going to be talking about is formal charge. And formal charge, how do we calculate that? Well, the first thing I want to say is that formal charge is very useful in identifying the total charge on a molecule. And so it's very important for that. It's also important for resonance, and we'll see that later. But what it is the group number minus the number of bonds minus the lone electron. And what do I mean by group number? So we see here, hydrogen is in group 1, beryllium in group 2, boron 3, 4, 5, 6, 7, and 8. So those are your group numbers. So for example, what if we had this molecule right here, right? Okay, and we want to find the formal charge on this carbon atom. And note this, formal charge is always for a specific atom. You can't say, what is the formal charge of a bond? You can't say that. Technically, you can say what is the total formal charge of an entire molecule, but it's not just considered formal charge alone. If they just say formal charge, then they're just speaking of one specific atom. So group number, well, if we look on the periodic table, carbon's in group number 4, minus the number of bonds. So 3 bonds, minus the number of lone electrons. And notice it doesn't say lone pairs. So the lone electrons are 2, alright? Which makes sense because this whole thing has an overall charge of -1. If you remember, carbanions always are, anions. They have a -1 charge, and so this is really how we find those charges. But pretty useful, especially when we want to find the resonance. So for example, resonance, what does that mean? It's the movement of electrons within a molecule. So something resonates all the time. If you have, especially if you have double bonds, the electrons are never just stationary. They're not just staying in one place. They're always moving around. So in this case, we have the electrons getting pushed up here, and in this case, we have the electrons getting pushed down. And they're always going back and forth. But the thing is, they're not 50%. They're not 50% in this, 50% in this. That's not the case. There's one that's more predominant than the other one, and you use formal charge to figure out which one. And so a lot of times I'll ask you, what's the most dominant molecule between these different resonant examples, and you have to choose which one based on these rules. So the rules are, for identifying which resonance structure is dominant, the first one, and very, very important, is every atom has to have an octet. And I would say that that's very true for almost every molecule. The ones we have to look out for that they do like to test are boron and sulfur. So sulfur, if we look, it has group number of 6. It can actually have 6 things going around it, and they're not linear like that. I'm just drawing that for you guys. And boron, which has 3 groups around it. But for the most part, we'll always be dealing with stuff like carbon, oxygen, nitrogen. Those are really what we'll be dealing with, and they have to have an octet. If they don't, it's still possible to have that molecule, but will it be the dominant one? Probably not. And the next thing to determine which is dominant is, does the formal charge match up with the electronegativity? And what do I mean by that? For example, we could potentially have this as another one, right? We could have these electrons going down. So right now we see like that, right? Potentially we could have this electron go down and we have negative and positive. Well, between these two right here, which will be the predominant one? Well, if you remember, we want the most negative formal charge to be on the one with the highest electronegativity. And this is where Fonkelbruch comes in handy. And so if we notice, O is much more electronegative than C, right? So O should have the most negative formal charge. So in this case, O has the positive one and C has the minus one. So that would not be the right one, right? Because in this case, the O has the most negative charge, most electronegative. That makes sense, right? Hey guys, remember to post any questions you would like us to answer in the next question of the day down below in the comments. Thanks for watching.